So now we want to find the last time we defined crossing number, and then we show that this holds, so which is approximately this. So now we want to find the lower bound, which is, of order 4, polynomial of n with degree 4. For that, let's prove this lemma. If we have a graph G, if it contains, say, A copies, so A is denoting the number, which is copies of a subgraph H, and each crossing in a drawing of G appears in at most B copies of H. Then we have the crossing number of G is at least A over B times crossing number of H. So for a proof, so we consider a drawing of G with exactly G crossing number of G many crossings. Then we do the double counting. Each copy of H in G contributes at least crossing number of H many crossings to the drawing, and each crossing in G is actually counted at most B times. So for each copy of H, you count the crossing in that drawing of H, which is a sub-drawing of G. And we do that for all copies of H. Then each crossing is actually counted at most B times. So B times crossing of G is at least C times A times crossing of H. So this proves this inequality. Then what do? We consider Kn, which is G, and consider Kn minus 1, which is H here. Then if you have this crossing, how many times, okay, so first we determine H. A is the number of copies of H in G. Then the number of copies of K sub n minus 1 in Kn is, you just choose one vertex and delete, so A is n. So B is the number of times that this appears in H. Then what you do is you take one vertex outside of this and then delete, and remaining thing is H. You choose other vertex, then you get other copies of H. So B is n minus 4. Then crossing number of Kn is at least n over n minus 4 times crossing number of Kn minus 1. From this, we can get crossing number of n is n times n minus 1 times until 6. And we multiply n minus 4 times until 2 times crossing number of K5. We already know this crossing number of K5 is at least 1. This shows that we have lower bound, which is n times n minus 1 times n minus 2 times n minus 3, and on the bottom you have 5 factorial, which is 1 over 120 times n to the 4 plus some lower order term. So we get the quartic upper bound and lower bound. And actually, in 1972, a guy named with Guy proved it is at least 1 over 80 n to the 4 plus some lower order term. The crossing number is at least that, and at most 1 over 64 n to the 4 plus lower order term. And give me a moment. So now let's, this kind of take care of the, not take care of, but this kind of shows the crossing number of complete graph is, order n to the 4. And exact asymptotic of this kn is not known. So these upper bound and lower bound are pretty much best possible. And for other general graph, which is not kn, can we find the general lower bound? For non-complete graph, we can prove still the quite a good bound, which is proven by these people. So when G is given, it has n vertices and m edges. If m is at least 4n, so which is a reasonable assumption as all the planar graph has m of 3n minus 6 edges, so a bit above that, then below that, we can apply the previous bound that we have proved in the last lecture. That's quite efficient. So we get this lower bound. So how do we do is we want to use some probability method. What we want to do is we have a drawing, then if you randomly delete some vertices, so we keep the vertices with the probability p, then then it's easier for us to remove the crossings than edges, and it's easier to remove the edges than vertices, because once you keep the vertices with p, probability p, a vertex is there with probability p, but the edge is there with the probability p squared. If one of them is gone, it's gone, so that we have to keep the both vertices to keep the edges. And to keep a crossing, all 4 vertices involved must be there. So with probability p4, p to the 4, it's there, and it's easy to get lost. So what you do is when you have a pretty dense graph, you randomly choose the edges with priority p, and then you see this graph remain, which is not deleted. There you find the relationship using the, say, Euler's formula. Then you get a much better relationship between the crossing number and number of edges and number of vertices. Let's make it more rigorous. We consider a drawing of G in the plane to obtain a lower bound on the crossing number of G. We take a random induced subdrawing H. We include each vertex independently at random with probability P. Let n prime be the number of vertices in the graph H that we obtain. N prime be the number of edges in H that we obtain. Then what's the expected number of n prime? Which is Pn, because every vertex remains with the probability P in, and the expected number of edges in H is P square M, because for an edge, if one of the vertices is deleted, it's gone, so both of them has to be there. By the linearity of expectation, this is what we get. I'll let Y be the number of edges number of crossings in the drawing that remain in H. Then what's the expected number of Y? For every crossing, the probability that is still there in H is P to the 4, since every vertex has to be remained. So this is what we get. The expected number of Y in H is P to the 4 times crossing of G. So we consider a drawing of G in the plane with exactly CR of G crossings. So let's say that that was our assumption. For 4 endpoints of the two edges must remain to keep the crossing. Then what do we have? What we have is that in this H, if we apply the previous theorem with Euler's formula, this, then what we get is that it always has at least m prime minus 3m prime minus 6 crossings as the maximal planar subgraph, has at most 3n prime minus 6 edges.
무슨 말씀을 하시는지 저는 잘 모르겠지만 원하신다면 웹에서 3m 프라임 6를
I'm sorry, that was the CD of my MacBook. where were we? Sorry. So it has at most, maximal planar graph has at most this many edges. So, this is what we get. Then, by the linearity of expectation, if we take the, this means that this is always non-negative. So if we take the linearity of expectation of this is again non-negative. And this expectation, if we take the expectation, this is again non-negative. Then from the linearity of expectation, what we get is this expectation of y is at least the expectation of n prime minus 3 times expectation of n prime plus 6, which is p square m minus 3 pm. Plus 6 is here pn, but 6 is not so important, we delete it. Then this implies that the 3n plus p cube crossing number of g minus pm is at least 0. So now we choose our p. Let p be 4n over m, which is at most 1, as we said that m is at least 4n. Then from here what we get is 3n plus 64 n cube over m cube crossing number of g is at least 4n. So this implies that crossing number of g is at least m cube over 64 n square. So this proves the bound that we want. And this theorem is best possible up to constant, multiplication of constant. Yeah. For example, if you consider complete graph, then you can easily see that you cannot improve this bound too much. And it has some application in other areas, applications in combinatorial geometry. So one of the questions that Eldridge asked in 1946 is that if there is n points on a plane, and how many pairs of them has distance exactly 1 between. So determine the largest possible number of pairs on the plane when there are n vertices. Easy way is if you consider grid, then with every distance 1, 1, 1, and then choose these endpoints, then you can get like 2n pairs plus some constant. If you take grid points with but now you choose this distance in a more careful way and not taking all the points, and you just take the points which are from the right distance from the origin, then by doing that, it actually show that we can put the n points on the plane so that there are at least n to the 1 plus c over log n many unit distance. So this is actually, I mean, so this is 2 to the log n times 2 to the log c log n over log n. And this is n, and this actually also goes to infinity as n goes to infinity. So this is super linear, but this is also smaller than any n to the 1 plus epsilon for any epsilon positive. Because as n grows, this gets smaller and smaller. So at certain point, it's smaller than epsilon. So this is n to the 1.1 plus log of n. Then, so this shows that we can put vertices so that, I mean, we can put points in a clever way so that we have at least this many number of unit distance. Then, in order to prove the upper bound, how can we prove upper bound? And if you consider, I mean, this graph, if 2 points has a distance 1, then we add an edge, we add an edge, we add an edge, we add an edge. Then you get a graph. If their distance is not 1, then we don't add an edge. In this graph, if you have 2 vertices, and you have the distance 1 to other vertices, then these 2 vertex u and v has a common neighbor. The number of common neighbors of these 2 is at most 2. Because all the neighbors of this lies in on this circle, which is distance 1 from u, and all the neighbors of u also lies on this circle, which is distance 1 from v. Then common point is only 2. If you take 2 circles, they intersect at most 2 points. So u and v, its common neighborhood has size at most 2. This means that it doesn't have k23. And we know that I mean, in the undergraduate graph theory, we learned about Turan's, I mean, number, extremal number or Turan number, which is that the maximum number of edges in on graph which doesn't contain this k sub 2, 3 and have a n vertex graph. So from that, we actually know that we learned that this is at most, I mean, subconstant times n to the 3 over 2. So this shows that we have for upper bound for this is at most some constant times 1.5, which is a bit far from here. Eridish's conjecture is that the right maximum, right number, is some function which is very close to n but a bit bigger. And Samoredi in 1973 actually showed that this is strictly smaller than n to the 3, 2. It's some function which is little o of n to the 3 over 2. He used some complicated argument using regularity lemma. And later, Spencer, Samoredi, Trotter in 1984 proved big O of n to the 3 over 4, which is a better bound than n to the 1.5. And secondly, gave a short proof of the same fact using the above theorem. So we prove this here. There are at most 4 times n to the 4 over 3 unit distance pairs among a set of endpoints in the plane. Let's prove this. So you have this endpoints, and if say there is some point which, so we, for every point with the distance 1, we pair them up in this way. But if there are some points which is not paired up with anything, then we can actually move this towards some direction until it becomes distance exactly 1 to some point, and then we can add the number of distance. So by moving points or pairs, and also if there is 2 points which are distance 1 but it's not, it's not paired up with any other, then we slowly move to one direction until one of the points becomes exactly distance 1, and then we stop there. So it means by moving a point or pairs without actually reducing the number of pairs at distance exactly 1, we can actually ensure that each point is involved in such a pair, and that no 2 points have distance 1 only from each other. So this we can ensure. Let P be an optimal endpoint configuration. With Q unit distance pairs. So assume you have endpoint configuration with Q unit distance pairs where Q is as many as possible, and we will obtain a graph from P. But instead of just putting H between 2 vertices with distance 1, so we will not do this. Instead, what we do is we have one vertex and another vertex, then from here you draw a circle, unit circle centered at here. So, and this point you again draw a unit circle, and this point you again draw a unit circle, and for this point, say you draw a unit circle. You keep do this. So we obtain a graph from P by drawing a unit circle around each point. If a point in P is at distance 1 from, say, K other points in P, then these points partition the circle into K arcs, meaning that we have this 1 arc, 2 arc, and this one, this two. 1, 2, 3. And 1, 2, 3. So each of them are considered to be, edges. The resulting 2Q arcs. So every time, so by our assumption, every circle contains at least one other vertex. And we said that Q unit and also we can assume that if there is a one point which has distance 1 to 1 point and then no other, so in the case that this has this unit circle which has only one point on this circle, in that case what we can do is we can take this and then we rotate it a bit. Give me a moment. So we rotate it in this way. As we assume that these two are not the only points which are distance unit distance. This has another point with distance 1. So if you slowly rotating at certain point, you get that this distance is again 1. So by doing that, you can assume that every vertex, every point here has at least two other points. At least two other points which are distance 1. So once you put this unit circle, you can assume that every circle contains at least two vertices, 2 points. And every time you have a pair with a distance 1, then this increase the number of arcs by 1. So we can actually get 2Q arcs. These are the edges of a multigraph which doesn't have loopless multigraph G. This is a multigraph because if we have these two, then we have this edge and this edge between 2 points. So it could have multi-edge, but it doesn't contain a loop because no circle contains only one vertex. In this case, this is a loop, but we assume that every circle contains at least 2 points. Since 2 points can appear on 2 but not 3 unit circle, G may have edges of multiplicity 2. But no larger multiplicity. Meaning that if you have 2 vertices and then the unit circle passing through both of them are either this or this. Give me a moment. I'm now a bit confused in wait a moment. I think in this case we can have these 4 edges. But if in such a case, I think, I mean, if there is no more vertices on here, then we can move the entire 4 vertices until one of them give me a moment, let me think. Let's just say, yeah, multiplicity at most 4. Give me a moment. Each time. Yeah. So I will change this number a bit later, but okay. I think, yeah, this has at most, I mean, 4 multiple edges. Am I missing something? There could be this and here, so that we cannot really move. Okay, yeah, let's say 4. So, for no larger multiplicity. So what we do is we delete one copy of, we delete 3 copies. Let me double check one more time whether I'm actually missing something. Yeah, okay. If I delete the 3 copies of the each duplicated edges. To obtain a simple graph G prime with at least say Q over 2 edges. So we can assume that Q is at least say A then. Otherwise, I mean, the bound already holds. Let's say this bound that we want to prove is A times n to this fourth third. Otherwise, the bound already holds. So, because these lines, these arcs lie on n circles, I mean, they cannot produce too many crossing. Because each pair of circles crosses at most twice. So, in this G prime, after deleting some, we can still have some many crossings. And on this, I mean, on this drawing, so by removing the certain arcs, we get this simple graph G prime and drawing on it. So some of the, I mean, edge is deleted, some of the part of the arc is deleted, and some of them are not. And Q of too many edges, I mean, edges remain. Thus, the drawing of G prime has at most 2 times n choose 2 crossings. Then, by the previous theorem, what do we know? Crossing number of G prime is at least Q to the 3. So, Q over 2 to the 3 and 64n square. So we have that 2 times n to the 2 is at least Q over 2 to the 3, 64n square. So this shows that Q cube is at most n times n minus 1 times 64 times n squared times 8. So Q cube is at most 112 times n4. So Q is at most 8 times n 4 to the 3. So this proves this upper bound. So this is one application of the crossing number to combinatorial geometry. So now we move on to the next topic, next section.